So now that we've done a full review of inverse functions in my previous video, you can now look at applying this to inverse functions for trigonometry. So, as you just heard, there was a video prior to this that really dove deep into inverse functions and inverse operations. I highly recommend that you watch that video before this one. So what we are going to do now is talk about the three inverse functions that are most commonly used in trigonometry. This is the inverse sine function, the inverse cosine function, and the inverse tangent function. And as explained in the previous video, what we do with inverse functions is to undo an operation. Now, as a quick reminder, this is an example of an inverse sine wave. Okay, that's like a sine wave, basically where the x's and y's are switched. Here is an example of an inverse cosine wave. Again, an example of where instead of this going high, medium, low, medium, high, it's the x's and y's are switched. Here's an example of the tangent function. And the tangent function has asymptote lines here and here. And you can see all of these in the previous video that I made. Now, again, creating these inverse functions is a matter of switching the x and y positions. So here is y equals sine of x, where the x and y's are switched, and so that creates the inverse function graphs that I've made over here on the left. And here's my x and y switched for cosine, and here's my x and y switched for tangent to create these graphs. Now, the domain of the inverse sine is going to be from -1 to 1, as explained in the previous video. And so is the same for our cosine wave. And we can just kind of logically figure that out because a normal sine and cosine wave would have a range between -1 and 1. And so this domain then becomes the restrictive area. Whereas this goes infinitely up and down, so the range is infinitely long, as is cosine. Because you can imagine the sine and cosine waves be like springs that just continuously move up and down. It's not the same thing for tangent though, although tangent does go left and right forever and ever, so it's all real numbers. But there's a restriction for tangent, and the restriction for tangent goes from its asymptote lines from -π/2 to π/2 exclusively, which means we cannot actually touch these asymptote lines here and here at +π/2 and -π/2. Now, we are going to restrict our inverses to 2 quadrants, and the reason why is because we only want 2 answers for each of these problems, a positive answer and a negative answer. If we didn't restrict these to 2 quadrants, then we could have 2 answers per, like we could have multiple answers for each problem. So this is something you'll need to memorize, that the sine only goes between the first or the fourth quadrant. The cosine only goes from the first or the second quadrant. And tangent only goes first or the fourth quadrant. Now, the reason why we should take a look at our unit circle on our x and y axis is that a sine is a representation of y, and therefore we have positive sine values here and negative sine values here. So that's why we're choosing the first and fourth quadrant. Now, cosine is a little different because cosine is an x value. Oops, sorry, should put my y there, not there. Sorry about that. I know it's an inverse function, but so my y is positive there, my y is negative here, and here on my x, I've got an x and negative x here, negative x, positive x. So that's why we're going to look at the first and second quadrant for our cosine. And then if we look at tangent, tangent makes sense because we have those asymptote lines, and the asymptote lines are here and here, so we're going to, again, take our positive and negative for our tangent, first and fourth quadrant. So again, we are restricting our inverses to these two quadrants. First and fourth for sine, first and second for cosine, first and fourth for tangent. So it is very important too that right now you get out your unit circle. Your unit circle is going to be critical in solving for theta or eliminating any kind of trigonometric identity, because we are either going to be finding the location or we're going to be finding the value. So taking a look here, this says, based on your previous page's pictures, you can see why domain and range restrictions exist. For the following exercise, evaluate the expressions. So what I'm going to do is I'm going to translate to you what this actually means. We're going to have an answer that's going to be very, very nice and specific. And what's best about this is this inverse is finding a location. So inverses find locations. Inverses find locations. So we're going to have this location right here, but this is actually asking a question. In quadrants 1 and 2, and the reason why I knew quadrants 1 and 2, because we're talking about inverse cosine, in quadrants 1 and 2, where is cosine of theta? And your book might use the letter T here. Where is cosine theta equal to 1? Okay, so what I'm going to have to do is grab my unit circle, which I happen to have here, and find out when is my cosine equal to 1. So if I'm looking exclusively at the first and second quadrant, my cosine of theta equals 1 at 0 degrees, or 0 radians. We're going to answer our problem in radians. So my answer to this problem is 0. Because there was no other space in quadrants 1 or 2, or frankly on the unit circle, where the cosine of theta is equal to 1. And I can see that right here on my unit circle. Oops, that's a little bit too here because I'm looking at a PDF. Sorry, I can't get too specific, but you can see at 0 degrees and 0 radians, cosine of theta is equal to 1. Okay, so now here we have the inverse cosine of -1. So this is asking again, in quadrants 1 and 2, where is cosine theta equal to -1? Okay, so we go back to our unit circle here, and we see at pi, cosine is equal to -1. Cosine's not equal to -1 in any other place. So this means that my answer here is in pi. Now let's continue this line of questioning here. It's now going to ask about an inverse tangent. In quadrants 1 and 4, you'll notice I had to change because I'm not talking about cosine anymore. In quadrants 1 and 4, where is tangent theta equal to -1? So where's tangent theta equal to -1? Okay, so now I am going to look in quadrant 1 or 4. Well, since it is a negative, I'm going to look in quadrant 4. And when is tangent equal to -1? It looks like tangent is equal to -1 at 7 pi over 4. Now, what's important about you trying to write down the answer, because I bet there's going to be a few of you that say, hey, Mr. Anderson, what I did is I wrote down in my homework 7 pi over 4, and I kept getting the problem wrong. Like I looked in the back of the book, it didn't match, or more importantly, I tried in my online homework and it kept saying no. Well, the reason why this is the wrong answer is it violates the range. Notice that the range goes from negative square root of 2 to square root of 2, and 7 pi over 4 does this. Okay? You see 7 pi over 4 goes too far because we have restrictions. We can't actually go beyond this or this green line. So what we have to do is find the equivalent angle to 7 pi over 4, and what we use is the reference angle. Reference angles, going back to Unit 1. So this is not the right answer. I'm sorry, I was writing in the wrong blank. My apologies. Well, you had to erase it anyway, because 7 pi over 4 is not the correct answer. No, the correct answer is negative pi over 4. Now, yeah, we would never usually write negative radians. We would usually write a positive radian, but in this case, we have to show the angle and that location of that angle that doesn't violate this range policy. So now we have to be a little bit tricky about how we do things. Now, problem 4 is a lot easier than problem 3. Problem 3 definitely had a trap in it because you were in the 4th quadrant and you had to write the angle correctly to fit the range requirement. But here, the tangent is positive, so you have to basically try this problem on your own. Pause the video and see if you can get the problem right. Okay, hopefully you have, and this is saying in quadrants 1 and 4, I'm using these ditto marks so I don't have to write all this out again. Where is tangent theta equal to square root of 3 over 3? Well, luckily, since it's positive, we're going to be looking in the first quadrant, because the first quadrant's positive for tangent, and square root of 3 over 3 for tangent is right there at square root of pi over 6. So your answer here is pi over 6. And pi over 6 is definitely between negative pi over 2 and pi over 2. So that feels pretty good. Now 5 and 6 are tricky problems. They are made to be difficult. And they're made to be difficult because they take you into the 4th quadrant, and these 4th quadrant locations are, yeah, they're a little bit tricky because you want to write down that 4th quadrant. So let's, instead of writing down all the words, let's see if we can just get to the answer. Where is the inverse sine negative square root of 3 over 2? Okay, so let's look in the 4th quadrant, since we can only look for sine in 1st and 4th quadrant. Negative square root of 3 over 2, inverse, so we're looking for sine. Okay, here we go. We have it at 5 pi over 3. But we can't write down 5 pi over 3 because 5 pi over 3 is bigger than negative, basically positive square root of 2, or positive pi over 2 and negative pi over 2. So we're going to put down negative pi over 3. Because negative pi over 3 is the same equivalent terminal side of your angle as the positive 5 pi over 3. So this is your answer. Now what I'd like you to do is I'd like you to try problem number 6, pause the video, and try to do it yourself. Looking up a where in the 1st and 4th quadrant where the sine is equal to negative square root of 2 over 2, that's going to be right here at 7 pi over 4. And we've been here before, right? We've been here. We've literally been there for problem number 3. So our answer for this problem is negative pi over 4. So what's the moral of the story? Is look for range violations. Now that's not really a problem with inverse cosine because you're not going to be stepping out of your zone there. But you will have some pretty big issues with inverse sine and inverse tangent, and you bet that's going to be on the test. Now to end this video, we are going to use a calculator to find the value of each of these expressions rounded to 2 decimal places. Now, please make sure you have your graphing calculator here. Now, you don't need a graphing calculator. I mean, you could use like a normal calculator, but for the graphing calculator and the normal calculator, click the mode key and make sure that you are in radian mode. Now, this is the default of all graphing calculators, so that's kind of nice. So now what I'll do is I'll click second mode, and I'll use the calculator to get these values. And since when I do this here, the calculator goes away, so I won't be writing these down, but I will be showing you the answers here. So if I go trying to find the inverse cosine of 0.6, I can click the second button and cosine, and then type in 0.6. I can close that off for good programming, and my decimal is 0.98. Or sorry, 0.93. I looked at the wrong one. Okay, to do inverse tangent, I click the second and the tangent key and type in 0.2, and close that off, and this gives me 0.2, because rounding this to 2 decimal places would round this to 0.20. Second sine, and now I'm going to type in 1 divided by 8, and these are all in radians, of course, and you're wondering, like, well, how do I know that they're in radians? Well, they don't have degree symbols by them, so they're in radians. So this inverse sine of 1/8 of a radian, which is 1/8 of a 57.3 degree angle, is 0.13. Now, arctangent is just another way of saying inverse tangent, and I just wanted to show you that. So if I have the inverse tangent of 3 radians, which is roughly 3 57.3 degree angles, this gives me negative 1.25. And for our last click of the video, inverse cosine is going to be of negative 0.44, and this is going to give me an answer of 2.03. So here we've learned about translating inverse functions, and we've also done some calculator work. Stay tuned in the next video. We are going to look at doing some elimination, or as you would say, canceling of trigonometric functions.